Suresh is a senior NVH engineer at Volvo Trucks, located in Greensboro in North Carolina. And his presentation will cover a concrete method to evaluate the acoustics performance of the pillar foam in a truck cab. So welcome, Suresh.
I hope everyone can see my screen, and welcome all. I'm Suresh Patra. I'm the senior NVH engineer over here in Volvo at Greensboro, North Carolina. I'm taking a different route. Here, what I'm going to show, there was a joint study done with the ESI North America regarding the analysis of pillar foam, or you can call it as a body cavity fillers also, as it's normally called in the automotive side. Just to give a brief introduction, these foams are quite extensively used in the automotive side. But on the commercial truck side, within Volvo North America, it was not being used. So we were kind of thinking of using it in future products or in the current products. And that's why this analysis was kind of done to see what are the benefits of using in the commercial truck side. So the objective was to develop a SEA, basically statistical energy analysis template model using VA1, the software provided by ESI. And also the major tasks were to basically see with and without the fillers. And then we also measured surface pressure loads on the cab. This was done previously, and also, like I said, to evaluate the load cases with and without the fillers. So the load cases for this simulation were we used a standard load case, which was the surface pressure across the panels throughout the cab. And then to better understand the cavity filler performance, we also included a tire patch load case, which is basically putting a 1 watt acoustic power in the tire patch location. And then we also did analysis to look like blocking the big panels, and just to see how the noise transfers through the body cavities only. And the two cases that were analyzed were without the fillers and with the fillers. For this study, initially we had 2 fillers, basically 2 foam materials from different suppliers. And the buyout properties of this foam materials were estimated using FoamX software from ESI. Going forward, looking at how we built the template model was we had the FEA model of the sleeper cab. This is what we call as a sleeper cab. And then the FEA model was loaded in the VA1 software, where we created the whole SEA panels. And then also over in the top, you can see the body in white. These are the pillars. This is the A pillar, B pillar, C pillar, and all the other pillars. But for our study, only the A, B, C, and those rear wall pillars that were considered where we will be putting our foam materials or the cavity filler materials. Then we created the interior and acoustic SEA cavities. Over here you can see. And after that, SIPs were created. SIPs are nothing but the semi-infinite fluid. Essentially, these are connected to the exterior cavities so that we create a diffuse field. Essentially, there's no reflection back. If there is any sound transmission, there's no reflection. Sound radiation is not reflected back. So that's what the SIPs are for. And in the lower half, you can see the different cavities that were generated. So we divided the whole inside cavity into six small cavities, sub-cavities, I would say. Basically, one is the front and the back and the sleeper section. In the sleeper, we had a rear upper cavity, the mid and the lower. and for the front we had the driver upper cavity and then the head space and the leg space. This was created so that we can have a better understanding as to in which cavities the noise is coming from, and also in the SEA, since it's spatially averaged values, so the better, the more number of cavities you have, the better averaging you will get. And over here we show the locations where the baffles or your fillers were placed. So you see it was the lower A pillar, then the upper A pillar, and also in the head space over the driver ear, and then the B pillar, C pillar, and also in the rear wall pillar. So this is just a driver side view. So there were 6 in total, 6 on one side. So in total there were 12 cavity fillers used in the study. Going to the results. So the first results over here is the normal load. Basically, we had all the measured surface pressure applied on the panels, like you see on the top right-hand corner. All the excitations are shown over here. And here we see the results for the 2 foam materials. Both the foam materials kind of gave this same trends, and also you can see there was very marginal difference between the overall sound pressure level with and without the fillers. Going forward, when we looked at the contour plots, what we see, if you look at the picture on the right hand top corner, what we see is the pressure levels going inside are decreasing. So essentially there is some absorption happening from the pillars, but then this absorption is not a significant absorption which would create some deviation in the overall sound pressure level, and that's why you see a very marginal difference between with and without the fillers. Going forward, discuss the results that we had with the tire patch. So you see the excitations over here on the tire patch location. This was just to study more in depth, and here only we considered only one foam material, because like in the previous slide, we saw the trends are similar, so that's why we use only one foam material. But with this acoustic power also, we didn't see much difference between with or without the pillars. And also if you look at it, again the same absorption we are observing, and also in the front part where we are seeing the difference. In the rear, in the sleeper section, we're not seeing because what we have, because of our loading, which is mostly in the front part, not on the rear. So that's why you see a decrease in the sound pressure level in the front section rather than on the sleeper section. And like I said, we went further ahead, and basically what we did was when you develop the SEA cavities, we have the area junction. So the area junction between the interior cavity and the big panels. By big panels, I mean to say the door panel, the side panels, the firewall, all these big panels, the area junction between them was turned off, and only the area junction between these cavities, the body in white cavities, was turned on. So essentially there was no energy transfer from these big panels. The energy was only been transferred through these small panels. This was to see if you are getting the effect or not. And with having done this, what we see is essentially we see some good difference between with and without the pillar. It's 0.5 dBA. Now you have to take in consider that this is for the whole cab. So it's I won't say pretty significant, but then we see some difference over here when we are transferring only through the body cavities. Essentially, we also have looked into the energy transfer plots. From the energy transfer plots, what we see was most of the sound energy was being transferred from these big panels rather than going from the body cavity. And one of the reasons is because I think the cross-section area of these body cavities are smaller than what you have for the panels. And that's why there is much more energy transfer from the big panels than this acoustic body in white panels, body in white cavities. And that's where in the initial results, we were not seeing a significant difference between the sound pressure levels. Also, what we did was for the initial simulation, we had these fillers of just 1 inch thick. So basically kind of mimicking a baffles case of scenario. And then we tried different thicknesses. We went for 50 mm, and also we tried to fill the whole cavity with the foam. This is the results, again, the same on the contour plots. So here we see for the foam thickness, what we see is, again, the same trend follows. Like when we have the blocked panels, we see a significant difference between with and without the filler. But there is, again, some difference with and without filler if the foam is completely filled in the body in the body cavities. So our conclusion from this study was that the SPL, the difference between the SPL does increases as the foam filler increases, and then, like I said, there's much more energy being transferred from the big panels, and that's why we don't see much effect of the filler foam. And also, one thing I would like to add is in this matrix, because in Volvo, our interior noise matrix is a sound pressure level. So we were using the sound pressure level as the matrix. But then in future study, the other matrix, like the sound quality matrix, there we might see much more effect of this filler foam on the sound quality matrix than on the sound pressure level, because it's more of a, what I think is more of a frequency phenomena also. So they might be attenuating certain frequencies, so you will see some difference in the sound quality than the overall sound pressure level.